Hello there, Mr. Sutton here with the BC Calculus 710 Extra Practice number 6 solutions on alternating series test. For this problem, we want to know which of these options here, the alternating series test, can be used to check for convergence on. So recall the AST says that you'll converge if your terms are alternating and decreasing in absolute value to 0. And that's all it says. So we need the alternating, and we also need this decreasing in absolute value to 0 business. Well, alternating, we've got that with all three options. They all have this -1 to the n plus 1 term going on in there. How about decreasing in absolute value to 0? If we take a look at option 1, n over n squared plus 100, well, that is going to be 0 if you take the limit to infinity, so that's a yes for that option. For option 2, limit of this expression without the absolute value. Doing this, we can ignore the 3's, so it's basically just n over 100n, which is 1 over 100. That's not 0, that's not decreasing to 0. It might be decreasing, but not to 0, so this is a no, it does not meet the AST conditions. And for option 3, well, this one's kind of weird. So this one, the term is going to be, the non-alternating part is going to be 1 over n if n is odd, 1 over n squared if n is even. Well, let's consider what would happen if we just plug in a few values of n. So for n equals 1, you just have 1 over 1. For n equals 2, you have 1/4. But then for n equals 3, you have 1/3. Now, these things are supposed to be getting smaller, which is to say your denominator should keep getting bigger and bigger compared to the numerator as you go. But 1/3, which comes later on in the series, is actually larger than 1/4. So with option 3, you're not consistently decreasing, so that's also a no. So then only option 1 works, giving us choice B. For this one, we want to know which of these series converges. So you'll notice that these are all alternating, so they at least meet one condition of the alternating series test. Really, it's going to come down to which of these are decreasing in absolute value to 0. So let's just take the limit of each one, and whichever ones aren't decreasing in absolute value to 0, those are probably going to fail the nth term test anyway. So taking the limit of this first one, this is essentially going to be -n over n, which is -1, but then we have this -1 to the n out in front, so basically you're getting plus or minus 1 one way or another. That's not 0. So this one fails by the nth term test. For this next limit here, this is, if you ignore this 1, essentially n over 2n. So we have plus or minus 1/2 if we reduce that, which is not 0. So this also diverges by the nth term test. Option C, well, now we've got the limit of n squared over 3 radical n. This one, as you approach infinity, this one's actually going to go to plus or minus infinity, which is not 0. So again, diverging by the nth term test. On this last one, we have a bottom-heavy function here. So we're alternating. Our terms are decreasing in absolute value to 0. The limit of this thing is going to be 0. So therefore, this one's going to converge by the alternating series test, and we pick choice D. So for this free response, we have this series here, which looks kind of weird. For one thing, we've got a random p-value in there, which we don't even know what it is, other than it's greater than 0. But we're going to work with this. For the first part, they're giving us a p-value of 3 and an x value of 8. And they want to know if that resulting series converges absolutely, conditionally, or if it diverges. Well, let's start by actually seeing what this series looks like with p3 and x8. So we've got -1 to the n plus 1, and then we're going to have 8 minus 3 to the n over 5 to the n times n to the third. And I can reduce and simplify this a little bit. 8 minus 3, this is going to be 5 to the n. That cancels out with this 5 to the n down here. So when all is said and done, this is really -1 to the n plus 1 over n cubed. All right, so this is the series we're trying to figure out if it converges absolutely, conditionally, or diverges. We first consider the absolute value version of this, so basically 1 over n cubed. This series is a p-series with a p-value of 3. Since that's greater than 1, this converges absolutely by the p-series test. For this part, we're given a p-value of 1 this time around. X is still going to be 8. We want to know if that series converges absolutely, conditionally, or diverges. So let's see here. I've got basically everything I had in part A. I have an 8 minus 3 to the n, but now I've got an n to the 1 downstairs. Simplifying this, we again have 5 to the n, canceling this 5 to the n. So now we have negative 1 to the n plus 1 all over just n. So again, considering the absolute value version of this, which is just 1 over n, this is the harmonic series, which diverges. So this does not converge absolutely. How about we consider the alternating version of this then? So negative 1 to the n plus 1 over n, that is the alternating harmonic series, which we know converges. So we can say that this converges conditionally by either because it's the alternating harmonic, or you could say by the alternating series test, either one of those. On this part, we're given x equals negative 2, and we want to know at what value of p, which they're not giving us yet, does this series converge. All right, so let's plug in negative 2 for x and see what happens. Simplifying this a little bit, this is really negative 5 to the n. So I can think of that as just being negative 1 to the n times 5 to the n, and then that 5 to the n and this 5 to the n down here would cancel, leaving me with just a negative 1 to the n up here, along with the negative 1 to the n plus 1 that I already had there. If I combine these negative 1s, I can basically make this negative 1 to the 2n plus 1. Now, negative 1 to the 2n plus 1, you're basically guaranteed that no matter what you plug in for n, you're going to get an odd exponent. So this is always going to be negative 1 in the numerator then. Now, to go a little bit further and start reasoning about the value of p, I can factor out a negative 1 from this summation, so just pull a negative 1 outside. And then inside, I just have 1 over n to the p. Now, this is a p series. Since this is a p series, it's going to converge if this p-value here is greater than 1. And since they were asking for what values of p does the series converge, well, we just answered that, and here's the reasoning. For the last part of this problem, when p is 1 and x is 3.1, we're told the series converges to s. They want us to use the first two terms of the series to approximate s, and then use the alternating series error bound to show this approximation differs by s by less than 1 over 300,000. So let's start by plugging in 1 for p and 3.1 for x. So I have 3.1 minus 3 to the n, and this is going to be n to the 1 if I change that up a little bit. And just going to clean this up a little bit so it's easier to work with. 3.1 minus 3, that's 0.1, which is also 1/10. So we essentially have 1/10 to the n. I can combine that with the 5 down here to the n to be 50 to the n in the denominator. And this n to the 1 is just n. So there's what the cleaned up version looks like. So they wanted us to use the first two terms of this to approximate s. Okay, well, if we plug in 1 and 2 for n, let's plug in 1 for n to start with. So that's negative 1 to the 1 plus 1, so positive 1, over 50 to the 1 times 1, so basically 1 over 50 when all is said and done. So I'm going to say s is approximately equal to the following. So starting with 1/50th, and then if I plug in 2 for n, well, now that's going to be negative 1 to an odd power, so negative 1. And downstairs we have 50 squared, which is going to be 2,500, times 2 is going to be 5,000. So we have minus 1 over 5,000. I could stop here, at least for this part of the problem, because this is all constants. But if I really wanted to, I could simplify this. This is really 100 over 5,000 minus 1 over 5,000, so 99 5,000ths. Now we have to show that this approximation differs by the real value of s, differs from the real value of s by less than 1 over 300,000. And they told you how to do it. They said use the alternating series error bound. So to actually do that, let's set up the conditions of this. To use the alternating series error bound, you need to have an alternating series whose terms decrease in absolute value to 0. Well, we look up here. This is definitely an alternating series. since it is a bottom-heavy function, we have basically all the growing stuff in the denominator. This will decrease in absolute value to 0. So the terms of this alternate and decrease in absolute value for 0 for sure. That means that the error is going to be less than the absolute value of the next term. So that is the alternating series error bound that we're stating here. That means specifically the error is going to be less than the absolute value of whatever this is when you plug in 3 for n. Because the next term, I mean, this last term we had was an n value of 2. So the next term is an n value of 3. And we don't need the -1 stuff anymore because it's absolute value. So we're just going to have 1 over 50 to the third times 3. We need to show that this is less than 1 over 300,000, though. And you can't just write that this is less than that. You have to simplify it a little bit so that you can reasonably see it's less than 1 over 300,000. So what do we have here? 50 to the third. Well, 50 squared, that's going to be 2,500. 2,500 times 50, well, that's 5 times 25 with 3 zeros after it, so 125,000. So we're multiplying that by 3. That's going to be 1 over 375,000. Since 375,000 is a larger denominator than 300,000, that means that this fraction is smaller than 1 over 300,000. And that proves what they asked us to prove here. On this free response problem, we have a positive constant p, and we're given this series 1 over n to the p that diverges. First task is to figure out if the series 1 over n to the p squared converges or diverges. Well, since this original series diverges, and it's a p series, that tells us that this p-value must be somewhere between 0 and 1, including 1. Well, if p is a value like this, then if I square a number like that, I'm going to get another number that is also between 0 and 1, including 1. So that means that 1 over n to the p squared, since it's 1 over n to a number between 0 and 1, is going to diverge also by the p-series test. For this part, they're asking if the series -1 to the n over n to the p plus 1 converges absolutely, conditionally, or diverges. So we first consider the absolute value version of this, 1 over n to the p plus 1, to see if we can get absolute convergence. The key on this one is they told us p was a positive constant, so that means p is greater than 0, which means that p plus 1, if I add 1 to each side here, p plus 1 is going to be greater than 1. That means that this series is going to converge by the p-series test, because you basically have n to something that's bigger than 1. Well, if this converges by the p-series test, this was the absolute value version of the series they gave us. So that means that this series in general is going to converge absolutely. For the last part on this problem, they want us to evaluate the series from 1 to infinity of 1 over x to the p plus 1. Now we know from part B, where we evaluated the series version of this, that this whole thing is going to converge to some number because the series on which this was based converged by the p-series test, but we actually have to figure out what it converges to. So let's start, since we have an improper integral, by rewriting this with a limit. I'm going to have the limit as b approaches infinity of integral from 1 to b of all this stuff. And I'm going to rewrite this with a negative exponent. So basically this whole exponent multiplied by -1, negative p minus 1, just to make my next step easier. My next step is to take the antiderivative of this. So just using the reverse power rule, adding 1 to this exponent, I just get negative p. And then dividing by negative p, I have -1 over p times x to the negative p. And I'm evaluating that from 1 to b. Still have my limit as b approaches infinity. To make my life even easier, I'm going to factor out this -1 over p from my evaluation. So I have limit b approaching infinity, -1 over p is now being taken out of there. And now I just have to plug b and 1 into this x to the negative p part. So this is going to be b to the negative p, which I can write as 1 over b to the p. And then we're going to be subtracting, let's see here, 1 to the negative p, so minus 1 over 1 to the p. And at this point, well, as b approaches infinity, this first term in here, this 1 over b to the p, this is going to 0 because this is bottom heavy. This next term is just going to be 1 over 1. So basically we have negative 1 over p times negative 1 after we apply that limit. And this just multiplies out to 1 over p, which is our final answer.